Welcome back to another USIS Axiom video. Have you ever wondered how a computer can recognize your face, identify a cat, or even drive a car by looking at the road? How can a machine actually see? The answer lies in one of the most powerful inventions in modern artificial intelligence, the convolutional neural network, or simply CNN. CNN changed everything. They gave machines the ability to process and understand visual information almost like the human brain does. So what is CNN? Before CNN, there was flattening that went from two-dimensional to one-dimensional, which deleted the spatial information. People noticed that it is weird that the information is still the same even when the position is changed. That's how they thought of the convolutional layer, which maintains the spatial data. A convolutional neural network is a special type of deep learning model designed for images and visual data. Unlike regular neural networks, which treat an image as just a long list of numbers, CNNs preserve the spatial structure, the width, height, and depth of the image. Imagine you're looking at a picture. Your eyes don't look at the whole image at once, but they scan it piece by piece, detecting edges, textures, and shapes. CNN works in a very similar way. The method they use is something called a convolutional filter, a small sliding window that moves across the image. At each position, the filter multiplies pixel values by small weights and sums them up. This helps the network detect local patterns, like lines, corners, or even eyes and noses. The filter is also called the kernel in the window. After each convolution, the model usually applies an activation function, like ReLU, which keeps only the most important signals and adds nonlinearity so the model can handle complex patterns. Then comes pooling, which compresses the image representation. It reduces the size while keeping the essential information, making the model faster and more robust to small variations in the image. Finally, the CNN passes the extracted features through fully connected layers, where it learns to make a final decision, such as classifying whether an image shows a dog, a cat, or a car. Also, stride is moving one by one to the right or to the left or upward or downward, and padding is filling the surrounding area with zero so that the information at the corner parts wouldn't be dismissed. So to summarize CNN, the progress is input to padding to convolutional layer to pooling to convolutional layer again and to pooling again and repeat, and finally flattening and output. So, in simple terms, CNN is digital eyes that detect patterns layer by layer. From simple edges to complex objects until the computer understands what it's seeing. Now let's look at the history of CNN. The history of CNN is a story of breakthroughs that shaped the entire field of computer vision. What's important about history of CNN and why we need to know it is how they did it and how they thought of that idea. The progress. It all began in 1998 with LeNet-5, developed by Yann LeCun. This model was designed to read handwritten digits from bank checks. It was small, efficient, and a true pioneer in using convolutional layers for pattern recognition. Although computing power was limited back then, LeNet proved that neural networks could see. LeNet used pooling, padding, and fully connected. Fast forward to 2012, the year everything changed. This was when CNN gained fame and attention until today. That's when AlexNet, created by Alex Krizhevsky, won the ImageNet competition by a massive margin. AlexNet used GPUs for fast computation and introduced ReLU activations and dropout layers to prevent overfitting. This model didn't just outperform others, but it crushed them, cutting classification errors in half and igniting the deep learning revolution. To be honest, it was almost a copy version of LeNet, and it just increased in size. The increased size also led to the overfitting problem. The overfitting problem happens because with a small dataset, the computer learned narrowly and just memorized. To solve this, AlexNet tried to use a dropout layer which randomly switches off the neurons to stop the memorization. They also thought of batch normalization, that using 0 and 1 is the best way. Then came VGGNet in 2014. They thought the deeper they made, isn't it better? So let's stack it really deeply. That's the deep architecture. But that also led to the Great Vanishing problem. The Great Vanishing problem is the more they give to the front, the information vanishes. It's like rumors. The more it spreads, the more it vanishes. They tried to solve this using pre-training and weight initialization. And they also did object detection and semantic segregation. Also in 2014, came GoogleNet, also known as Inception version 1. If VGGNet was thinking about doing more, GoogleNet thought about which layer size would fit the best. So they tried different layers like 3.3, 4.4, 5.5 and so on. It introduced the Inception module, where multiple filters of different sizes like 1x1, 3x3, and 5x5 operated in parallel, allowing the model to capture features at multiple scales simultaneously. It also used auxiliary classifiers and bottleneck structures to reduce computation while maintaining accuracy. Bottleneck structure is decreasing the size of the channel and then increasing it again to combine all the information. You can just think of the neck of your water bottle. The auxiliary classifiers is like a teaching assistant who are placed in between to check your process and maybe tell you that you are wrong to fix beforehand and help. In 2015, ResNet took things even further by solving the vanishing gradient problem. Finally, it added skip connections, which let gradients flow directly through the network, allowing models to reach unprecedented depths even over 100 layers. The res came from residual, a residual line that is a shortcut for inputs. It gives the x and only learn the f, x, to do, f, x, plus x, so that it can give the information until the end. ResNet fundamentally changed how we build deep networks today. Finally, in 2017, came MobileNet, a breakthrough in efficiency. It introduced depthwise separable convolutions, splitting the convolution into two simpler steps both depthwise and pointwise, making CNNs light enough to run on smartphones and edge devices without sacrificing too much accuracy. From LeNet to MobileNet, CNNs have evolved from simple, slow networks to incredibly deep and efficient architectures that power today's AI. Today, CNNs are everywhere. They power face recognition on your phone, self-driving cars that see the road, medical imaging systems that detect tumors, and even robots that navigate the world. They've become the eyes of artificial intelligence, teaching machines not just to calculate, but to truly perceive and understand. So next time your phone unlocks with your face, or an app identifies your pet as a golden retriever, remember, behind the scenes, it's CNN doing the work. From LeNet to AlexNet, from GoogleNet to MobileNet, CNNs have evolved from recognizing digits to recognizing the entire world. They are not just algorithms, but they are the digital eyes of the 21st century. Thank you for listening to this CNN video and hope we meet at the next video.